Welcome you again to the third lecture of the multivariable calculus. So in this last lecture, we came to know what is the limit of about the multivariable calculus. Now in this lecture, we'll know about the continuity. Okay. Now, if you have suppose one function f of xy that I already discussed in the last two lectures, that here we'll have more than one independent variable. So x, y and y are the two independent variable here, and suppose that it is continuous at the point a and b, then the limit at this of this function at the point a and b should be exist, and it should be equal to that exact value at the point a and b. Now for this case of if I write this function, if this write this thing in the terms of uh, what is say in the terms of neighborhood term, right? Then I can write as mod of f of xy minus l is less than epsilon whenever x comma y minus a comma b is less than delta. So here we are considering the point a and b. So that is the only difference between the limit and continuity. In the limit, it should not be equal to that f of ab. It might be some other value. For the continuity, it should be, this limit should be exactly equal to the f of ab. Okay. Now, some important result of the continuity that you already seen for the case of the single variable. So suppose you have the two function fxy and gxy, that is the continuous at some point a and b, then the sum of this function, so it should be x and y, and here it will be g of y, is continuous at this point a and b. Similarly here x and y and g of x and y, the product of these two functions should be also continuous at the point a and b, and the last one, that function of f of xy and g of xy should be continuous at the point. And then from the third point, that provided that g of xy should not be, functional value should not be 0 anywhere in the neighborhood of this point a and b. Okay. Now let's take some example of the continuity. Suppose we have this function f of xy. It is defined like that: x squared plus y squared, where xy is not equal to 0, and here it should be equal to, sorry, so it should be equal to, okay. So when the xy is not equal to 2 comma 2, then this value is x squared plus y squared, and when xy equal to 2 comma 2, then its value is 2, and we have to see whether it is continuous at the point a and b. We have to check. So for this continuity, we have to check whether limit at the point 2 comma 2 of this function is exactly equal to the functional value, that is 8, right? So if I take the limit of this function as x tends to 2, y tends to 2, then our function value should be x square plus y square, because when it is not equal to 2 comma 2, the functional value is x square plus y square. Now it is a polynomial, so it is continuous, so I can put the value x equal to 2 and y equal to 2, so it is 4 plus 4, that is equal to 8, and that is exactly equal to the functional value of 8, right? So I can say this function f of xy is continuous at the point 2 comma 2. Now let's check another example. So here we have given one function f of xy. It is defined in this way. Sorry, it will be equal to that when that xy is not equal to 0 0, it is xy by x square plus y square, and when xy equal to 0, then the function value is 0. Now I have to check whether it is continuous at the point 0 0. Okay. So if I approach this function, that is x y by x square y square, then if I put this value here, then I can see that it will be 0 by 0, so it will be undefined. So I can see I cannot directly put 0 0. So is there any way to check whether limit exists? So what I'll do here, I will approach to this point 0 0 by one straight line. Okay, if I suppose they plot this thing here, so you have x-axis here, right, y-axis here, and 0 0 we are finding the continuity of this function at this origin, that is here, right. So we are considering the xy plane, and this is your z-axis, right. Now, so this point basically 0 comma 0 comma 0, if I see in the 3 dimension. In the case of the 2 dimension, the z should be 0, so it will be anywhere in the xy plane, right. Not here, anywhere here, right, exactly here. Okay, so 0 comma 0 in the xy plane, so here it will be your the point. Okay, now I can approach to this 0 comma 0 in this way, right. Also I can approach the 0 0 by this x-axis. Also the negative of x-axis I can approach, also the y-axis I can approach similarly. So I can approach to this 0 0 point by various paths. Now I will consider any arbitrary path. Let's say, so I'll take one straight line. So I can take the straight line y equal to mx. So c won't be there because c will be 0, because this line should pass through this point 0 0, right. So the equation of the straight line will be y equal to mx. So this line will pass through this 0 0. Now you approach this function by this straight line. We are approaching to the 0 0 by this straight line. Now if I approach by using of this straight line y equal to mx, I am plugging in this equation y equal to mx. Okay, so x y equal to mx I am putting here, and here x squared plus y squared, that is mx squared, right. Now when y tends to 0 or when x tends to 0, then y tends to also 0, that is also holding here y equal to mx. So I can now see that there will be only one single limit, that is equals to x tends to 0. Now, so here x squared term will be there, the numerator, also in the denominator x square I can get common, I can cancel out because it is x tends to 0. Then I'll get m by 1 plus m square. So if I approach 0 0 point by this straight line, let's say y equal to x, where m value is 1, then at that time the value of the limit will be m equal to 1, so 1 by 1 plus 1, that is 0.5. Now if I approach, let's say y equal to 2x, so that is another straight line, right. Then if I put this value m equal to 2, so it will be 2 by 1 plus 2 square, that is 2 by 5, right. So if by choosing m defined value, the limit will be defined, so this limit is not unique, right. So this function is not continuous at the point 0 0. Now take another example. We have this function xy cube by x square y cube y to the power 6 when xy not equal to 0 0 and 0 when xy equal to 0 0. We have to find the continuity at the point 0 0. Now if I approach this function, let's say a arbitrary straight line y equal to mx, that is passing through the 0 0, then if I plug in the y equal to mx here, then I'll get x into y equal to mx, so m cube x cube and x square m x to the power 6, right. Now 1x square will be cancel out both terms, so it will be here. Now if I plug in x equal to 0 here, I'll get numerical to 0 and the denominator is not equal to 0, so limit is equal to basically 0. Now if I approach another way, we are approaching the origin using this curve x equal to mxy cube. I can approach this straight line also. So now I plug x equal to my cube here, so my cube, and here x equal to my cube, that's square. So then it will be m by m square plus 1. So I see that when we are approaching the 0 0 by this straight line y equal to mx, which is equal to 0, but if I approach the 0 0 by using this curve, then this value is not 0, that is depend on the value of m. So the limit is not unique. So I can approach the 0 0 point by various paths, right? Now if I approach one path, that is by using straight line, I am getting 0 limit value, whereas by using this curve x equal to mxy cube, it's giving the arbitrary value that is depend on the value of m. So the continuity thing is not happening here, so I can say this function is not continuous at the point 0 0. Okay, thank you.